Hey guys, so I know I've been a little bit slow on the uploading of videos here, but I did want to post a video covering some of the stuff that we talked about last couple weeks, namely including the death of stars, white dwarfs, neutron stars, black holes, supernovas, cool stuff like that. Because this is really fascinating stuff, and hopefully that you understand that as we go through the textbook. But if you're not seeing how cool these things are, I just wanted to go through and give my kind of 2 cents on all this stuff here. So first off, you guys have hopefully become familiar with this, but this is the general layout, the general scheme for how different types of stars evolve. So for low-mass stars that you see in the top there, you take a average star, a G-type, F-type, K-type or so. It goes through its main life, the main sequence of its lifetime. 90% of its life is in the main sequence. And then at the end, it goes from being a normal star, red giant, some stuff happens inside, and then it explodes. And for a small star, or even a low mass, medium mass, like our sun, that explosion is in the form of a planetary nebula, a gentle explosion of its outer layers of its atmosphere. And what you get left over is a white dwarf. Now for the bigger stars, these are the more interesting ones, because now we start off with an even bigger star, the O-types or the B-types, and it balloons into a supergiant star, just a giant star that's a little bigger than a normal red giant. But then when those things go kaboom, that's when all hell breaks loose, basically. That's when you have the supernova, the biggest, most violent explosions we know of in the universe. And from that, you get out either the neutron stars or black holes. And so the focus of this is on white dwarfs, neutron stars, and black holes. These are collectively called the core remnants of stars, or the stellar remnants. And you'll see why in a minute. So starting off with white dwarfs. So this is what any low-mass star will produce. Anything similar mass to the sun, a little bit more massive, a little bit less massive. And now during the main sequence of the star's lifetime, all that's going on at the core is taking hydrogen and converting it to helium. So you take 2 protons, convert it to a nucleus with, well, 2 separate protons, convert it to a nucleus with just a helium, 2 protons inside that helium versus 2 separate heliums, the hydrogen. So nuclear fusion of hydrogen to helium. Now, when it hits the red giant phase, that's when you start converting that hydrogen that it produced during the main sequence into carbon. You take 3 heliums, and it makes 1 carbon nucleus. And so you're producing helium during the main sequence, but now you start producing carbon during the red giant phase. And now carbon is as far as any star like our sun is going to go. It's never going to make anything more massive than carbon. But what happens is, during the final stages, we have the carbon that's been deposited towards the center. So at the very center we have the carbon. Now it's very hot there. Over 100 million degrees Kelvin at the center. And the only reason there's not fusion going on, there's not helium fusion going on at that center, is that there's just no helium left there. All of that helium at the core has been exhausted. But so you're at the core, it's just a big ball of inert carbon. The carbon's not fusing. But then if you go out far enough, in that shell around the carbon, now we start seeing enough helium nuclei that those things are going to continue fusing. So even though there's not fusion going on at the very center, there's still fusion going on in a shell around that core. And so we call it the helium burning shell, or the helium fusion shell. And then as we go further away from that shell, we got to a bigger shell, all the stuff outside of that helium burning is hydrogen. And that hydrogen is continuing to fuse into helium, and that helium in that shell is continuing to fuse into carbon. Now the carbon doesn't do anything more there. It just sits there. But you have these shells of fusion around that carbon nucleus, or carbon core. And so that's what a low-mass star looks like just before its final phases. And the final phase is, the explosion is what we call the Planetary Nebula. By the way, so the word for Planetary Nebula, it's kind of a misnomer, it's misleading. Basically, you go back 100 years or so, we had these older, less advanced telescopes, and you look out and you see, you're looking out at these fuzzy things out there. And back then, planets just looked like little fuzzy blobs. They move across the sky over the course of the year, but it's just little fuzzy blobs. Now, when astronomers first started seeing these explosions of low-mass stars, it looked exactly the same. It's just a little fuzzy blob, except it didn't move across the sky over the course of the year. But so these got the name Planetary Nebula. It's just a big cloud of stuff that looks like a planet through a telescope. It has nothing to do with planets themselves. It simply just looked like planets to the early astronomers. So just some confusion with the name, but again, nothing to do with planets. It just looked like them. So the Planetary Nebula happens when that carbon core, the very center of that, once you build up enough carbon in that core, there's no longer fusion going on in that core. So there's no more outward pressure. There's no more outward energy being given off because there's no fusion going on. So there's no outward pressure to be able to combat the inward push of gravity from the rest of that star. So that carbon core, which again isn't fusing anything, begins to contract. It's getting smaller. As it gets smaller, it starts to heat up. And what that means is, as that core is heating up, the carbon, it's never going to get hot enough to fuse carbon to anything else, but it will get hot enough to make that helium shell, the helium burning shell around the carbon, and that hydrogen burning shell around the helium shell. As that carbon core heats up, those shells heat up as well, and it makes way more fusion happen in those shells. The fusion rate in the helium shell and the hydrogen shell skyrockets here. What that means is there's actually way more energy being given off at the center of the star now than there ever was in the rest of the star's lifetime. So even though there's not fusion at the very center of the star, there's actually way more fusion going on in the hydrogen burning shell and the helium burning shell just because it's so hot there at the very end of its lifetime. Now eventually it reaches a point that so much pressure has built up inside that star, it's giving off so much pressure from those helium and the hydrogen burning shells, that the outer layers just balloon out so far that gravity can no longer hold on to them. And now at this point, slowly, in a series of bursts, those outer layers of the star are just gently ejected from being a part of that star anymore. So it basically goes through, it contracts a little bit and then gives off the outer layers of the star. Then contracts a little bit more, gives off the next outer layer. Contracts a little bit more, gives off the next outer layer of the star. A famous astronomer, Alex Filipinko, has termed this cosmic burps. The star is basically just burping out its outer layers of the atmosphere. It's kind of apt here. But so over time, enough of these bursts occur that all you're left with is just that main central part of the star. Again, the core is carbon, and there's helium fusion and hydrogen fusion going on around it. And if you wait long enough, one second. If you wait long enough, all of that hydrogen will have converted to helium, all of that helium will have converted to carbon, and all you're left with at the very center of that thing is just a dense ball of carbon. So I have some images here of Planetary Nebula, the gentle explosions from these stars. So just take a look at it. This is just kind of a generic planetary nebula. You see this fuzzy cloud of gas and stuff that used to be a part of that star's outer atmosphere that's been ejected. Now we see another one. This is, I think, the glaring eye nebula. You can probably see why that is. It just looks like it's an eye that's staring at you. And we can see all of that glowing stuff as outer layers of the atmosphere that have been expelled from that star. Not in a violent explosion, but just in a gentle enough explosion that now we can see all the rest of the stuff that used to be inside that star. Here's another one. This is called the Cat's Eye Nebula. I think this is pretty cool. You can kind of see the narrow cat's eye there. But here you can actually see the individual shells. Each time that planetary nebula expelled a little bit out of the atmosphere, we see many different shells of stuff expanding outward here. And this one, I think this is pretty cool too. It's the Hourglass Nebula. You can kind of see why that is. But so again, these things, because they're giving off their shells in a series of bursts and not just in one big explosion, we can see there's some structure here. This one a little bit less so. But now take a look at the very center of these as I go through. We see there's a dot at the very center there. Very center, a brightly glowing object. Very center, same thing. You can kind of, it's not quite in the exact center here, but you can still see a little dot there. What that is the white dwarf. It's the core remnant. It's what's left over from the core after the rest of that star has been exploded. And so for a low-mass star, that core remnant is a white dwarf. Again, all of those elements that have been converted from hydrogen to helium, from helium to carbon, all you're left with is just a big ball of carbon at the center of that. And it's very dense. You take essentially all the mass of the sun except for what's been expelled, so maybe a little bit less mass than what the sun has right now. You take a lot of that mass, condense it into something the size of about Earth. And that's what a white dwarf is. It's almost entirely carbon. It's very hot because all of that heat that's been produced during its lifetime is now trapped inside of it. And it's not quite hot enough to fuse carbon into anything heavier. So it just sits there, very hot, slowly evaporating its heat that it's built up all of its lifetime, slowly evaporating that away over the course of tens of billions of years. So these things are incredibly long-lived. Once our sun goes into the white dwarf stage, it's going to be there for probably another 80 billion years at least. So really cool objects. But it gets even cooler. So to understand this, we have to know why a white dwarf doesn't just keep on collapsing into nothing. So here's the core, and here's the carbon core. There's no fusion going on. It gets smaller, but at some point it stops getting any smaller. It's going to have collapsed to as small a size as it can. And the reason that it can't collapse any further is because of what's called electron degeneracy pressure, or electron pressure for short. And what this is basically normal matter is composed of protons, neutrons, and electrons. And the typical atom looks something, I'll have to go back, but the typical state of matter looks something like this. You have individual electrons surrounding protons at the core, and there's some neutrons and stuff thrown in there. But so it's the pressure of those electrons acting on all the other electrons around it that keeps that matter from getting any denser, from getting any smaller. It's, again, the electrons exerting pressure on all of the other electrons around them that doesn't allow this to get any denser. So let me go back a little bit here. And so again, the name for this is electron pressure. And this is what keeps a white dwarf from collapsing. You can't compress those electrons any further than they already are. You can't smush the electrons any closer to the other electrons. They repel each other. And that's what holds a white dwarf up, the electron pressure, or the electron degeneracy pressure. But for certain types of stars, you can go further. That electron pressure isn't quite enough to hold up certain types of stars. So let's go through and talk about how a high mass star evolves. So we go at the core during the main sequence, you're converting hydrogen to helium. Once the red giant phase starts, now you're converting helium to carbon, just like a low mass red dwarf, or red giant. But for a high mass star, now when that carbon core forms, there's so much more gravity there that the carbon core contracts and heats up, and contracts and heats up, and eventually it gets hot enough to fuse carbon into oxygen. So now you're starting to build up oxygen at the core. Over time, as more and more carbon fuses into oxygen, you end up with an oxygen core. And the same thing now happens. That oxygen core is pushed, it's compressed by all the gravity, it gets smaller, and eventually that oxygen core heats up enough to start fusing into the next heavier element, which is neon. And you go through the whole sequence, you build up a core, it contracts, it gets hotter, you start fusing the next heavier element. That core now, the new core, contracts, heats up, starts fusing the next heavier element. And so this is how all of those elements up to iron are produced. But the thing is, iron is the most stable element in the universe. You can't fuse iron into anything heavier unless you add in a huge amount of energy. A huge input of energy is the only way you can fuse iron into anything heavier than that. So it's not a naturally occurring reaction in the universe. There are no, with one big exception, there are no environments that have enough energy to give those iron nuclei enough energy to fuse to anything heavier. They're incredibly stable. They're just going to sit there, not do anything, once you create iron in the core. So you're creating iron in the core. Now at this point, the entire weight of the star is pushing down on it. It's heating up that core, but it will never actually produce anything heavier than iron. And so that core, at some point, once you reach a large enough iron core, it's being pushed on by all the gravity around it, and something kind of cool happens. So let's go through what happens here. Now here's typical matter. Again, what's holding these individual atoms up, as I've drawn them here, is the pressure of all the electrons pushing on all of the other electrons around them. You can't compress those into a smaller volume unless you were to overcome that electron pressure. But in these high mass stars, when all of the pressure of the entire star is pushing down on the core, you are able to overcome that electron pressure. And what happens is the individual electrons fuse, they get smushed into the nucleus, and they fuse with the protons. So those electrons get pushed into the nucleus, and you're seeing here all those electrons are being smushed into the nucleus, and they hit the protons, and they fuse together. You take an electron, you take a proton, smush them together, you get out a neutron. And that's what happens here. You go from electron pressure matter, fuse those electrons together with protons, all of those things now become new neutrons. So now you just have a huge ball of neutrons. Again, it's come from the fact that you have individual electrons and protons. If you apply enough pressure, which you can only have in high mass stars, you apply enough pressure, they smush together, and now the neutrons are much smaller than those atoms as we had before. So you're able to take all of this volume of matter, compress it into that small of a space. It's just very, very tightly packed neutrons everywhere inside that core now. And so once all of those electrons combine with all the protons inside of that iron core, now all you have left is a very, very dense ball of a huge number of neutrons. And so obviously that core is now much smaller than it was before, because you've basically taken away all of that empty space. Now it's just simply a huge ball of individual neutrons. And once those neutrons become packed enough, those neutrons are able to hold up that star. So now this is something called neutron pressure. It's kind of like if you take a huge, a rack of pool balls and you stack all of those pool balls up, no matter how hard you push, you can't make those pool balls any smaller because they're as closely packed, they're as tightly packed as possible. And that's what neutron pressure is. It's the pressure that those neutrons exert on all of the other neutrons around it in this incredibly dense, incredibly high pressure area of the core. And it's called neutron pressure. That's what holds up neutron stars. It's just a huge ball of neutrons all pushing against all of the other neutrons. So, when that core collapses, you're fusing the hydrogen with you're fusing the electrons with the protons to make a very tight ball of neutrons. What happens there is, remember, so at the end of a high mass star's lifetime, you have that iron core, but then you still have those shells of fusion going on around that iron core. Just like at the end of a low mass star's life, you have the carbon core and the helium and the hydrogen shells around it. Except in the high mass star, there are many more shells of fusion. But the point is, though, that core collapses. All of those shells try to collapse along with it. But here, what happens is those shells heat up incredibly quickly. There's a huge amount of heat built up, all just in literally a fraction of a second. So those shells become superheated. And the fact that those shells are trying to collapse, they become superheated, they all of a sudden start giving off huge amounts of pressure. There's what's called neutrinos are released. It's a little tiny particle that is created at the core of these stars. But so basically what happens, those shells contract, they become superheated, and they almost instantaneously just give off so much pressure that the star blows itself out from the inside. And it's basically what's happening is the core collapses, and the rest of it tries to collapse, but it can't because so much pressure is generated. So it basically bounces out instead. So it's this core collapse, and the rest of the star bounces out, and that's when the entire rest of the star explodes. All of those elements that are made all the way from carbon up to iron are just exploded into the rest of the galaxy in a split second. And that's called a supernova. The most violent events that we know of in the universe. Maybe unless you were able to merge two black holes together. But that's a story for another day. But so again, a supernova it's triggered by that collapse of the iron core, but it's brought about by those shells trying to collapse along with it until they get superheated and generate so much pressure in a split second that everything just explodes outward. And the cool thing is every single element that we have in the universe today that's heavier than iron is generated in that supernova itself. So there's this iron going on that's already there, and when that gets thrown out into space, those iron nuclei are able to combine with hydrogen, helium, carbon, everything else. You're now able to start building the even heavier elements than iron. The radioactive elements, uranium, plutonium, radon, xenon, all those very heavy elements are created in the supernova itself. Even all of the elements between carbon and iron, during that supernova happens, all of those are expelled as well. And so all of the iron in your blood, all of the carbon in your bodies, all of the oxygen in your bodies, these other elements literally were inside of stars at some point in the history of the universe. Your entire body, aside from maybe the hydrogen, helium, the trace amounts of helium you have, literally was at the center of a star at some point in the universe's history. Kind of cool stuff. As Carl Sagan said, one of the quotes I had a few weeks ago, we are all made of star stuff, quite literally. Every element in us heavier than helium was at the center of a star at some point in history. So, kind of cool. So anyway, the aftermath of the supernova. Most stars will leave behind a neutron star at the center of the supernova. However, for the very, very most massive stars in the universe, the stars that are more than 25 times the mass of our sun, so these are just the very high mass O-type stars, essentially, not even the neutron pressure of those very tightly bunched neutrons are able to stand up to gravity. So you have so much gravity pushing in, there's so much mass, that when that core collapses, you now have a bunch of neutrons. Not even those neutrons are able to hold up to that gravity. And so that core, it doesn't just stop when it makes neutrons. It keeps on getting smaller, keeps on getting smaller. And gravity collapses that core into a smaller and smaller volume until it's literally just a single point in space. So check out the diagram here. This might be meaningless, but so we're going from taking normal state matter, so electron pressure matter, convert it into neutrons, but then we're going to keep on compressing that into smaller and smaller volumes. And the end state is that everything gets pushed into a single tiny point in space. Just one point in space. It has no extent, it has no volume, it has no area. It's just condensed into the smallest thing possibly imaginable in the universe. And so if you take all of that matter that used to be inside that star, compress it into the tiniest thing you can ever get it to, that's when we have a black hole. So in order to understand exactly how these black holes work, we need to understand something called escape velocity. And the basic idea here, I'm going to show a series of pictures. The basic idea is in order to overcome something's gravity, you need to go faster and faster. So if we just throw a ball up from the surface of the Earth, throw it up at 10 meters per second, about 22 miles an hour. We just throw a ball up from the surface of the Earth, it's obviously going to go up and land back down on the surface. You throw it a little faster, it's going to go a little higher. Throw it at 100 meters per second or 200 miles an hour, it might get half a mile up in the air before it starts coming back down. But eventually it's going to hit the ground. You throw it even faster now, 1,000 meters per second. Now it's going to go a fair ways into the atmosphere, but it's still going to come back down and land on the ground. It's not until we throw it at about 11,000 meters per second. 1 second here. It's not until we throw it at about 11,000 meters per second that you can completely escape the gravity of the Earth. And that's what we call the escape velocity. It's the speed that you have to throw something, or the speed that something has to be traveling at, to completely escape the velocity, or to completely escape the gravity of the Earth. And not just for the Earth. You can apply this to any object. On Earth, the escape velocity is about 25,000 miles per hour. On the Sun, it's even higher. On white dwarfs, it's very high. But neutron stars, it's immensely high because you're making a denser and denser object. Okay, so the point is, the denser the object is, the stronger its gravitational pull on its surface. So the faster you have to go to get away from it. So you take all of the mass in the Sun, you compress it into something the size of Earth, you're going to have to travel much, much faster to escape the gravitational pull. Now you take all that mass and you keep on compressing it into the size of, let's say, the island of Manhattan. That's about how big a neutron star is. So when you compress it into that small of a volume, now you have to travel way, way faster to get away from its gravity. But a black hole is an object whose escape velocity is faster than the speed of light. That's what a black hole is. This is the best definition you can give for a black hole. It's something that's simply so dense, you have to travel faster than the speed of light to escape its gravity. And as Einstein said, nothing can travel faster than the speed of light. That's why a black hole is black. You simply cannot, nothing can escape the gravitational pull of a black hole once it's inside of it, because nothing can travel faster than the speed of light. So it's really not a fancy thing. It's not a weird, I mean, it is, but at its most basic definition, a black hole is simply just something that not even light can escape, because light can't travel faster than its own speed. So that's basically what a black hole is. But we can go a little bit further. We can look at how a black hole is made up. So at the very center of that black hole, where all of that stuff had condensed into, you take that core, it collapsed into a ball of neutrons, but it kept on collapsing smaller and smaller. All of that matter collapsed into a single point. That single point in space is now known as the singularity of the black hole. It has infinite density. And the reason I say that is that you take all of that mass, you collapse it smaller and smaller. The mass isn't getting smaller. What is getting smaller, though, is the volume. And that's what I mean by density. Mass divided by volume is density. So you take that same mass and you make a smaller and smaller volume. You're dividing by a smaller and smaller number. Eventually, you get to the point that the volume of that singularity is 0, which is crazy, but that's how it works. And so what happens is you start dividing by 0, and that's when the weird stuff happens. That's when you start getting an infinite density. That's when the physics stops working. So we don't really know how this singularity behaves, but we do know that it has an infinite density. And therefore, if you actually were at the very center of this thing, you would have to travel infinitely fast to escape it. But the good news is, the further you get away from the singularity, the slower and slower you have to go to escape it. If you go, maybe just a couple meters away from that singularity, now you don't have to travel infinitely fast. You only have to travel about 3 million meters per second. Still completely unattainable by anything in the universe, but it's not infinite anymore. Now let's say we go a couple hundred meters away from that singularity. Now the escape velocity becomes something a little more achievable. Maybe like 300 million meters per second. Still, speed of light is lower than that. So we'd still have to travel faster than speed of light. But if you keep on going further and further away from that singularity, eventually you reach a point that you only have to go the speed of light to escape. And so that's what's known as the event horizon. It's that distance away from the singularity where the escape velocity is exactly the speed of light. If you're inside of that event horizon, you have to travel faster than the speed of light to escape it. So once you get inside of that event horizon, you can no longer escape the black hole. But as long as you stay outside of that event horizon, you don't have to travel as fast as light to escape it. So outside of that event horizon, you're golden. You can just fire on the burners on your rocket ship or whatever. As long as you can get up to 90% the speed of light or whatever, you can escape. So outside of that event horizon, you're not being sucked in. You just have to travel really freaking fast to escape it. But once you pass inside of that event horizon, that's when the escape velocity, the speed that you'd have to travel to get away from that singularity, becomes higher than the speed of light. And again, that's why a black hole is black. Everything inside of that event horizon, you can't see. And you can't communicate with because nothing can travel faster than the speed of light. But you can still communicate with someone who's outside of that event horizon. You can fly close to that event horizon, but then turn and escape the black hole. Or you could even have a planet orbiting that black hole outside of the event horizon, and it'll just keep on doing that forever. So it doesn't suck everything in. It only sucks things in that go inside of that event horizon. Outside of the event horizon, again, it's the same thing as if you just had a really massive star there. And then, by the way, the textbook points out something called the Schwarzschild radius. Tough to say. That's just a fancy name for how far the event horizon is from the singularity. It was essentially invented or discovered mathematically by Karl Schwarzschild, who was I believe, a German physicist, and he was actually the first one to solve Einstein's equations of relativity. Einstein actually couldn't even solve his own equations. He just wrote them. Karl Schwarzschild solved them, and he realized that there is this thing called the event horizon. Inside of it, you have to travel faster than the speed of light. So, kind of a cool history thing. So, anyway, at this point, hopefully all of your heads are kind of blown. It's really cool stuff to talk about, and these things actually exist. We have discovered these black holes out there. Your textbook goes through a few examples. Cygnus X1 is a big one. That was the first one that was discovered, and it was also the subject of a Rush album in the 70s. But anyway, we have discovered these things in the universe, so they're not just crazy things that professors talk about. They actually are out there, and we've seen evidence that they're there. Obviously, we can't see them directly, but we've used indirect means of detecting them, and the book does go through some of that. So, if there's any questions, obviously, please let me know. I love this diagram. It's Cookie Monster debating or contemplating a black hole. But yeah, if there's any other questions you guys have about this, please let me know, because this is really fascinating stuff to talk about, and I feel bad that you just had your textbook to go from for the previous week. So I did want to make a video about this, but hope things are going well, and as it gets a little bit closer to finals time, I will be updating some stuff on D2L as far as information for the final exam and everything.